Great. Welcome to the ZUCMAP talk of this week. As you can see, the topic today is from mathematical finance to moral hazard, and in the talk, I will talk a little bit more about what those terms mean actually, and So, what is the idea behind this talk? As many people might have already seen, like a lot of talks until now were like really physics orientated and really showing like one specific side of what you can do in mathematics or in physics or like in calculus. And what I saw was like there was really not enough about probability theory, which is also a beautiful subject with mathematics. So I wanted to take this opportunity to show you a little bit of the other side of mathematics, what you can also do. And I would also like to thank the organizers, Nora, Sid, and Johan, who are sadly not here today, for giving me this opportunity. Yes. So what are we doing today? There are three major topics that we will be looking at today. So the first one would be the principal agent problem. This is a problem from contracting theory that maybe some people already know from economics, and which is now also discussed with the tools of stochastic calculus and like more mathematically rigorous tools. And in the second part, it will be about those tools. So and then we will introduce the stochastic modeling part, which will be about what tools do we have out of probability theory that we can use to model random processes that we encounter in finance, but also in other areas of life. And then we will apply those tools and introduce some basic results from mathematical finance, such that we can see how those tools are classically used, and also just as an example on how they actually what the definitions are about. And then at the end, we'll come back to the principal agent problem and see how the finance tools are also applied to the economical problem. And then we will consider a simple case that we will hopefully solve at the end if the time is not running out. So let's start with the first problem. So the principal agent problem, I will shortly introduce what's all about. There are two actors in the principal agent problem. One, the principal, and one is the agent. And the idea is the principal wants to hire the agent to do something for the principal, and the agent does this job and then gets some payment from the principal. So what's about is those two people want to find a contract such that the principal gets the perfect output generated by the agent, and the agent does not really have to work so much but gets some money from the principal. So we have those relations. The principal hires the agent does something for the principal, but both two people have some self-interest which they are following, and the question is, how can we like combine those two self-interests into a common contract? So this is like a well-known problem from economics, and or maybe a little more details about what we have. So basically, since both of those two parties have their own self-interest, we have two problems that we need to solve simultaneously here. So at the one side, we have the principal's problem, which is that he wants to offer the agent some contract that motivates him to do what the principal wants him to do. And in some cases, the principal cannot directly control the agent, so he has to design some kind of contract that makes the agent make the agent actually want to do the thing the principal wants him to do. So this requires some thought into the contract. And so what is like the optimization problem of the principal? Basically, he wants money, or he wants some value of something, and the value he gets is the output function that the agent generates. But of course, like since he has to pay the contract, he will lose the cost of the contract. So this is the one side of the problem, and so we optimize over all admissible contracts, whereas admissible contract will be something we will define later. We can also look at the agent's problem. So basically, what the agent does is he can perform something to improve the output function for the principal. But obviously, the agent has to work for it, so it's like the agent is normally very lazy, so he doesn't want to work. So he has some cost function that comes with managing the output. So basically, he has to decide whether he wants to work more and get more out of the contract that the principal offers, or he wants to work less, and then he has less cost to manage the output. And yeah, so we again have an optimization problem, but this time over all possible controls over the output function. And the question at the end is, what is an optimal contract? So there are two different formulations of the problem, and we can see that the second best case is the mole hazard case, which is exactly what we've already seen in the title. But let us first look at the first best case. It's the risk-sharing case. In this case, the principal knows everything about the agent. Imagine the principal really watches the agent 24/7 and can see how many hours he works or like how he performs. So he is able to observe the action of the principal is able to observe the action of the agent, and the payment, the contract payment, is also allowed to depend on this action explicitly. And so basically, since the principal can now control the agent, it becomes a one-sided optimization problem where the principal alone controls the action as well as the contract. And we have some constraints because obviously at some point the agent will simply quit, because if you don't pay him anything, he will just leave. So we have some constraint that the agent will stay in the whole game. In the second best case, which is a little bit more interesting, where we also have the two-sided optimization, the principal is not able to see what the agent does, or the principal is not allowed to contract upon it. So basically, there is some additional risk in the whole problem because the principal has not all of the information he needs to find a perfect contract, and therefore he needs to predict the action of the agent to decide what contract he wants to offer. So this is the problem we want to look at, and in order to do so, we need some math. And so math is mostly about some nice pictures and some beautiful lines. And here we can see a stochastic process, which we will come back later to. So we will see those again. First of all, what is a stochastic process? This is like the most fundamental object that we consider in stochastic calculus, or generally in stochastic modeling. A stochastic process can be seen as some family of random variables indexed by some index set I. And I in this case, or I normally, is simply the set of natural numbers, or, oh, this should be a 0, but yeah, or like the non-negative real numbers. So basically we have a one-sided line of discrete times or continuous times, and we define a stochastic process as a family of random variables over a common probability, over a common probability set, which means that we have a common probability measure that applies to all of the random variables. And basically, for a fixed event out of the probability space, we get a trajectory, like we can then plot the whole thing with respect to the time, and then we get a path. And also the random variables can have like values in any measure space, but normally this measure space would simply map into the real numbers, since it correlates to some kind of output process or some kind of price. So yeah, this is an example for a stochastic process. Here we have the random walk, which I hope most of you already saw in the probability lectures. So basically what this means is if we take one of the paths, at every point of time, we have the probability 1/2 to go up, or the probability 1/2 to go down. And then for different events in the probability space, we get a lot of different paths, which are shown here. So this is a very simple kind of stochastic process. And like for every time step, we get another random variable, which is distributed accordingly. So here we can also put in a little bit more math. where we can define it on a common probability space. You would consider a probability space that contains a sequence of random variables that are either 1 or -1 with the probability 1 divided by 2. And you can also show that such a probability space actually exists. So we are not talking about some zero or some empty set or something. And then you can simply define a random walk by a sum. And then you can clearly see that at every time step it goes up with probability 1 divided by 2 or down. And we can also find some more complicated random walks. For example, we can change the probability with which the walk goes up or goes down, and then we get a drifted random walk. So basically it's the same as normal random walk, but it's an expectation, or like with a high probability it will go up or go down in the end. Yeah, this is like a simple example. Now we can also define this discrete stochastic integral for discrete stochastic processes, and the most common example for discrete stochastic process is the random walk that we saw earlier. So basically we have two stochastic processes. We have xt, which is our random walk, and if we already include it in the context of mathematical finance, xt will denote the value of a stock that we want to trade on or something we want to bet on, like in the casino. This is something that goes up randomly. And ht is another process, and this will denote how much of the process we own, or how many shares of a stock we have right now. And the idea behind a stochastic integral is, given a stock and the number of shares you have at a certain time, it will give you another process, and this process will be your wealth process. So this process will tell you how many, what the value of your portfolio would be at some time t. And it's given by this relatively simple formula, since at every time we will get the increments of our stock times the number of shares we own. So basically, if the stock goes up by 1, so xi minus xi minus 1 is equal to 1, then we will simply get the number of shares that we own as profit to our wealth process. So yes, this is then the discrete stochastic integral, which we will be generalizing afterwards, also in the continuous case. Yes. So now we come to the continuous case. So basically, we can also consider stochastic processes which are not indexed by the natural numbers, but by the positive real line or the non-negative real line. And here, the most famous example for a discrete stochastic process, for continuous stochastic process, would be the Brownian motion, which is the red line we can see here. And you can see at every time step it can go up or down, but like those are really tiny increments which add up to the whole curve. The blue line is simply the red line with the drift. So at the end, it's a red line plus a linear function that goes up. Yeah, maybe a short definition to the Brownian motion. You don't have to read everything here. It's more or less about the idea behind it rather than the actual mathematical formulation. But what's important is that it's a stochastic process on a probability space, and we have 3 properties that the Brownian motion should fulfill. The first one would be that it starts at 0. So this is also something we have already seen here. The starting point has to be 0 for every Brownian motion. I will quickly jump to the last one because it's also a bit shorter. And there's a second mistake on the slide. So the Brownian motion should be almost surely continuous. So and almost surely means that with probability 1 it should be continuous. And this is also something we see here. So the Brownian motion has no jumps at any time with probability 1. So this is also something we need to impose. And now maybe for the most important property of the Brownian motion, which would be the second one. And this one means that the Brownian motion has stationary and independent Gaussian increments. So basically what this means is if we take any sequence of times, then the differences that we have in the process those are independent Gaussian variables. So let's go back to the picture. If we consider, let's say we take this point of time and let's take t1 as 0.5 and t2 as 1.0, then we can see that the difference between this point and this point, this one has to be a Gaussian random variable, and it would be independent from any other increments we could find along the curve. So any tiny point is also a Gaussian random variable, so it goes up with a certain percentage and down with another. Yes, but it's not so important to know all the details. Maybe here's another theorem to give a little bit more intuition behind the Brownian motion. Also here are a lot of mathematical details that you don't have to understand. If you want to consider a bit more in detail, you are invited to read everything. But basically, if we take a simple random walk, as we have seen beforehand, like this is a discrete process, and we define the following process, which is simply some kind of interpolation of the random walk together with some scalation. So basically, the simplest case would be we consider epsilon equal to 1. Then it would simply be the random walk with some lines drawn in between the values of the discrete process. And what we then do is we scale the whole thing time-wise by epsilon squared. So we take the whole walk, the random walk, and make it like, put it all together. And then we also multiply it by epsilon to bring the altitude down. And we can also see that epsilon squared is really necessary here, which is also something you can see afterwards in the lecture, if you take the lecture about Brownian motion. So yeah, we simply take a random walk and we put it a little bit denser together, and then we can see that the whole thing converges to a Brownian motion. Like it's a convergence in distribution for which is also the convergence you see at this at the central limit theorem. But basically, what this means is that the paths more or less look like a Brownian motion, and then this is also some other characterization of it as a limit of random walks. Yeah, so we come to the stochastic integral now, which is the discrete stochastic integral, but in continuous time, which is a generalization of also a generalization of the Lebesgue-Stieltjes integral, which I hope most of you have already seen in measure theory, which you can define on an increasing function or also on a function with bounded variation. Basically, it's the same as the Lebesgue-Stieltjes integral, which also in some way multiplies the increments of the function you integrate over. But we have to be a little bit more careful because our output should be another process that represents the profit if we invest into a Brownian motion. So basically, the output is a process, and also the Brownian motion is really wiggly. So we also have to be careful that the whole thing converges and it's finite. So we have to do some extra discussion on it, which I will omit at this point. But basically, the idea is the same one as behind discrete stochastic integrals. If we integrate over a characteristic function, and this would mean we buy, let's say, one share of the Brownian motion, like the Brownian motion is in stock now, we buy one share of the Brownian motion at t1, we sell it at t2, then our value at the end should be wt, should be the value of the Brownian motion at t2 minus the value of the Brownian motion of t1. The wedge here is simply the minimum operator. So what this means is after t2 we have the difference, and beforehand it goes with the Brownian motion, obviously. And so this would be the most simple case. Then we can, quite similarly to what we have seen in measure theory, when we define the different integrals, we can expand our definition to linear functions, linearly to simple functions, which are some kind of Serre functions, for example. And then by some convergence, we can define it for general purpose, for general processes. And then we have some kind of convergence, which is a bit more technical, but at the end, we simply get what we want. So two simple examples are here. If we integrate over a constant process, let's say C, then we simply get the Brownian motion with some factor in front of it. And this is also some other integral, which is quite common. If we integrate the Brownian motion itself, then we get this process. But this is simply an example. So let's continue with the last important thing we need in the stochastic modeling part. What are stochastic differential equations? I think many of you may already have heard of them. So technically, we have some kind of coefficients here, b and sigma, where b denotes the drift of our stochastic differential equation, and sigma would be a measure for the volatility. So the drift just tells us, like, deterministically how much we will technically go up or go down. This is some deterministic thing, and the volatility controls the amount of randomness in our system. So sigma is a factor in front of the Brownian motion, and so if sigma is big, we take a lot of Brownian motion, so we have a lot of randomness. If sigma is small, we have less randomness. And b is simply the drift that goes up or down. So if b is positive, we go up. If b is negative, we go down. And so we can like use the Brownian motion as an input of randomness to create a stochastic process with certain properties. And we also allow the coefficients to be dependent on the stochastic process itself. And this is what makes it an SDE, since we have to solve a differential equation with some randomness. We can also write the whole thing in differential form, which is a little bit more beautiful. So it would be dxt plus this term. And so the idea is to control drift and volatility. And there are a lot of results on this topic. And we know that existence and uniqueness of a solution is given under Lipschitz conditions, for example. And this closely relates to what we've also seen in calculus when we introduce like Picard-Lindelöf or the Cauchy-Lipschitz constructions. Maybe another example for what we can do with SDEs. So this is another SDE, the Umstein-Uhlenbeck SDE. And you can see the drift is more or less constructed that the process will come back to mu when it leaves mu. So if xt is like really up above mu, then it will go down back to mu and conversely. And then we add some randomness into the whole system, but we see there's not much changing here. Basically, the drift pushes the process back to mu, and the Brownian motion wiggles a little bit along the way. This is what we can do with SDEs. Now to the second part, what can we do with the whole machinery that we've just introduced? And this is where we get to financial markets, or how we model financial markets with the whole stochastic calculus stuff we did earlier. So basically, what stochastic markets are for us in mathematical finance, we have D+1 assets, which are simply stochastic processes, and we have one specific asset that is riskless. And you can like think about the riskless asset like a currency or like a numeraire, where you can like leave your money and it will not happen to there will not be like too crazy shit happening with your money. So we have an interest rate R that controls this your riskless asset, and it's in some sort predictable, but so like in some way you can see how your money will evolve. Then you have like D risky assets that we represent D stocks, and those are controlled by an SDE where you have given a drift process and a volatility process, and this is like by changing those variables you can create a lot of different possible ways to model actual financial market. And then obviously if there's a financial market, you want to invest in it. So what is a portfolio? A portfolio will consist of like one process eta, which will denote how much money you have in the riskless asset, or like how much currency you have right now, and delta, which would be denoting the number of shares you have in the ETH asset. So it's a d-dimensional vector that shows you how the number of assets you have in the risky assets. And then for a given portfolio, we can also construct a wealth process behind it, which simply means how much money you have if you liquidate all of your stocks right now. So basically, here we have the currency you have, the number of currencies times the value of the currency, plus the number of stocks you have times the value of the stock. And this is simply a scalar product to simplify the notation. So we have wealth product, wealth process, which we denote by X. And how does this process work? So we also get the dynamic behind the process, which is given by the self-financing condition. So we usually think that in a portfolio there cannot be money that gets in like at some random time or like gets out. So everything must be contained in the market. And like if you have too much money, it will simply be put into the currency, so it will not get out or something like this. And this is the self-financing condition. So your wealth will always be the interest rate times what you have in the currency right now plus the development of the stock and times the number of shares of the stock you have. So this is the dynamic of the stock market, and this is the interest rate. So this is how the wealth process goes. Now, the most interesting thing, or like one of the most discussed problems in the past of mathematical finance is how do we price derivatives, which is like a thing that that is frequently traded on financial markets. So basically, a derivative can be seen as simply a contract that you buy right now, which like you pay somebody else some amount right now, and the other person has to give you something back over the time based on the contract and based on the values of the stocks that you have on the markets. And we can simply model the payoff by some measurable function, where the measurable assumption is really just that, like some mathematical necessity. And so we have some payoff function g, which models the derivative. And we will consider some simpler derivatives. So we assume that our payoff will happen at some time maturity t, which we denote with a big T, and the payoff is given by g times a g of st, which is the value of the stock at the time to maturity. And one simple example would be European options, which are options that give you the possibility to buy an option or to sell an option for a price you've defined at the start of the option, and then we have like a call option. So at some time t, you can buy the option for price k, where k is already given at time 0, and so the payoff function would simply be st minus k with the positive part, since if this is positive, then you will buy it and make some profit. If it's negative, then you will just simply not use the option, and then your payoff will be 0 because you don't want to lose money. And the same can also be done with selling options, which would be a put option. So what is the price for such a contract? So if I want to buy such a contract right now, what do I have to pay for another party to give me the option to buy something at time t for the price k? So here also some examples to the options. This is the payoff function for the call option. So we just simply have the positive part here at some strike price k. And we also have to calculate in the price we pay for the contract, so the whole payoff function moves down a bit. The same thing we can do with a put option, and also there are more complicated options that you can design using the basic options. This, for example, would be a butterfly option, which you would buy if you are hedging that a stock doesn't change its value very much. So what is fair pricing? We want to price something such that it does not have any arbitrage. So basically, we don't want anybody on the market to be able to make some money without any risk. Basically, nobody should be able to design a portfolio such that he can definitely get some money over the time without the possibility that we will also lose some money. So basically, if I have something valued at 2 euros, I will definitely not sell it for 1 euro, because then I will lose something. So this is the basic idea behind fair pricing, and there's a lot of theory behind it, but just for the intuition purpose, in some specific markets, which includes, for example, the market we will look at afterwards, the expected value is one such viable price. So this is why we will look at the expected value in the next slide. and which would also be a fair price. So yeah, now we come to the Black-Scholes model, which is like a really famous model that started the whole stochastic calculus and mathematical finance thing. And basically, we just take the whole model we've introduced earlier and consider a really simple case behind it. So we, at the end, what we can see here in the market dynamics, we assume that the drift and we have a constant B, which controls the drift. We have a constant sigma, which controls the volatility. And then we get like independently distributed log returns that are simply Gaussian variables. And this SDE has a simple solution, which is the geometric Brownian motion. So here we can see it's simply some exponential of some random process. Yeah, and this is exactly what we've also seen earlier. So these curves are exactly geometric Brownian motions, which are exponentials of some sort of Brownian motion processes. And we can see that for fixed, we have a drift that goes up. So basically, every one of those things should go up. But here we consider different volatilities. And if the volatility is higher, it will bring the whole stock down again. So here we have different solutions to the Black-Scholes model plotted here. So yeah, then let's come to the Black-Scholes formula, which is like the breakthrough formula that showed mathematical finance that stochastic calculus is a proper tool to use. So basically, we want to price an European call option with this payoff, and for this we have to calculate the expected value. So basically, with the Black-Scholes model, we will get like a Gaussian variable. So ST is simply a Gaussian variable, and the log of ST is a Gaussian variable with this mean and this variance, which is given by the Brownian motion properties. And what we then do is simply, this is also something you've probably already seen in a lecture, we integrate over the density function, which is simply the normal Gaussian density function over for k until infinity. The reason is if the stock value is under k, then the payoff is simply 0, so we don't have to integrate over it. So we're only interested from k to infinity. And the whole thing can easily be resolved into this formula here, which is a closed form formula for the price of the option. And like phi is simply the Gaussian distribution function, which you can see quite commonly in probability theory. And then you get this formula for a possible price of or the price of a call option. And like this is the simple case, and we can also do this for different times. So basically, this is the price at time 0. We can also move. You can also buy the option at some other time and get another price. And then at the end, we get some kind of pricing partial differential equation, which is the deterministic equation that gives us the price of the option. And so why do we use Black-Scholes? Like it's quite simple models after we found the parameters. The parameters have to be estimated in some way by some statistical means, but afterwards it's like really simple to use, and it's even quite robust. Like I mean, like a constant drift and constant volatility, those are really not. It's like really not what happens in the real financial market, but we were able to observe that still it can give some good results if we use this model, and it also has a straight multidimensional generalization. So also if we have a lot of different stocks, that's no problem. And but it can obviously also be improved by changing the actual drift and volatility by modeling the actual market. So we can like change. There's a Markovian approach which uses continuous Markovian Markov change, and also we can consider random volatility processes or interest rate models if we want to generalize the whole problem. So yeah, these are some insights on mathematical finance about what you can do with SDEs and stochastic calculus and stuff. So, but now let's go back to the original problem, which was about the contracting problem between the principal and the agent. So here we follow the approach of this book here, which I will also show at the end of the lecture, and some paper where they've already did the special case we'll look at right now a little bit earlier. And the whole idea is the principal agent problem was already existent for a long time in the literature of economics. And then mathematicians came and said, oh, okay, let's do it in continuous time. And then everything kind of worked out because Brownian motions are really good to use and have a lot of beautiful properties. So we reformulate the whole thing into our stochastic calculus approach. Basically, the output process would be given by something like this. This is, again, another SDE. And V is simply some constant that we have here that denotes how much randomness is in our process. So basically, the agent could, for example, be managing a stock, which, and BT is a Brownian motion, even if W was the name beforehand. But yeah, so BT is a Brownian motion, and so there are some so there's some constant randomness in our system, but what our agent is able to do is he can control the drift of our random process. So it can control if it goes up or go down. And obviously, the principal wants the output process to go up. But the agent cannot observe the drift. So he has no way to telling how the principal has no way to telling how much the agent is actually working. So yeah, and again, we want the contract at time t, which is not allowed to depend on how much the agent is actually working. So how can we solve this problem now? We reformulate the problem a bit into our old framework. So basically, we introduce some utility function for the agent. This is quite important because like money is not always equal to money, and like really often in economy, like in econometrics or something, you have utility functions to denote how much something's actually worth to you. Or like if a stock is at some price, how much utility does it bring to you? And clearly the agent and the principal can have different viewpoints regarding how much something is actually worth. So we have different utility functions for the two parties, which is also something that makes the problem a bit more interesting. And we suppose there's like an exponential utility function, which means that when we have like, if x is like really low, then we have a really big difference in utility. So if we go from 0 to 1, from 0 to 1, there's a big increase of utility. But like if we go from 100 to 101, then we cannot see that much increase in the utility that we have, which is some assumption which probably maps the conception we have in the real world. And also we assume that we have some running cost that the agent has. So if he does something, so U is what he is doing, then it will result in some cost, which accumulates to this process here. And we assume that it's a quadratic cost because it makes the computations a lot easier. This is also something you've probably seen in classical mechanics, that quadratic costs are often easier to minimize or maximize in such problems. And so the problem he at the end have to solve is he considers his payment, which is given by the contract, minus the accumulated cost he has at the end, and this he puts into the utility function, and he wants to maximize it over a set of admissible controls that he has over the system. So this is the maximization problem that the agent faces, and at the end he will get some optimal contract that depends on the contract he was originally given. And there's like an individual rationality constraint, which simply means that he will quit if his utility is too low. And so we have the constraint that this utility or this expected utility has to be bigger than some constant that we fixed beforehand. So then the principal problem is, again, we introduce a new utility function that is also exponential, but it has another constant in it, which shows the different conceptions of the agent and the principal. And then we have a set of admissible contracts which need to fulfill that there is like an optimal control for the agent, and the individual rationality constraint has to be fulfilled for the agent. So this simply means he's not allowed to pay the agent too little, and then he has to solve the maximization problem of his own expected utility and which depends on the output process minus the cost the cost of the contract. And here we again take the maximization. So yeah, now we go back to the agent, and the problem is a little bit more challenging, so I will only delineate the ideas behind it. And for the agent, we can still see some of the stuff we can do. So what we do is we introduce the remaining utility process. So at some time t, what is the expected utility that we will get? The little t under the expectation simply means that it's a conditional expectation, which you've hopefully also have already seen, which simply means that given the information we have at time t, what will be the expected utility at the end of the time interval. And then since we have exponential utility, it's a lot simpler if we transform the wealth process with some log transformation, and then we add the costs, since it's a bit more difficult to discuss the cost in the whole thing. So this is another transformed utility we see. And we see that also that since for t equal to 0 or little t equal to 0, this is simply equal to 0. And the left side is simply some monotonous increasing transformation of the original utility. So instead of maximizing W0A, we can also maximize the transformed utility, where here there should be a 0 and not a t. So we transform the maximization problem, and then we get some stochastic differential equation. I will not go into the details here now, but like if we add some extra randomness by some process z, we can see that the whole thing is controlled, that at the terminal time, the utility is clearly given by the contract, and before that we have to subtract the running cost that the agent has, and then we get some extra randomness in the system. So this is the idea behind how we would solve this problem. And then with a comparison principle, this is something that you will also see in PDE lectures, literature, but you can also apply to BSDEs, like backwards stochastic differential equations, as you would minimize the thing and the deterministic thing. So we would minimize the drift to get like the optimal control. So at the end, you can find an optimal control this way. Yeah, for the rest, we will simply delineate some ideas. So the randomness can actually be plotted by this one. We get then another STE with that goes forward and not backwards. So now we have a condition at time 0. And so basically, we can control the wealth process, and the principal will also be able to control the starting point of the process. And this one has to be given by this because of the individual rationality constraint. Afterwards, and now I will also not go into the details, but the principal can reformulate his problem such that he targets some control U that he wants from the agent by choosing his contract. So since he knows what the agent will do after his optimization, he can like turn the whole problem around, and then we get like a classic optimization problem from stochastic calculus. So this is again a reformulation that we can already solve, and then we get the solution. If we plot in the actual function again, you don't have to get all of the calculations here. But the important thing is we can get an actual contract, so we get a solution to the whole problem in this simple case. So the whole thing is not like good for nothing. Yeah, so there is a solution to this problem, which also has some nice property regarding some special cases. Yeah, maybe in the last minute I will also talk about how we can where we can additionally go after the whole thing. We can add like more control possibilities and like more general cost processes. We can also consider different payment contracts. Like we don't have to pay the agent at the end, but we can also like pay him all the time. And also we could add more agent, and then it could also be tackled with like statistical physics tools to analyze this problem. Yeah. Okay. That's also already it for the talk. thank you for coming. If you have any more questions, you are happily invited to like ask them afterwards. And like here is the one book that I've mentioned, which is about contract theory. And yeah, thank you for coming.
First of all, thank you for the talk and that you came here. I just want to remind everybody that there's an apéro in the common rooms so that you don't forget that, and that there's a talk next week, same time, in here. There's more information coming on Instagram, and there is information on the website if you want to look at that.